All right. My name is Colin Arnott. I'm a junior computer science major, and this semester I did some mentored research with Professor Montek and Leandra. So the motivation behind this work is current image sensing has fairly low dynamic range compared with what, say, the human eye can do. Most screens are going to output about 8 bits, and the cameras are going to get probably about 12 bits maximum. And they're also going to be limited to a frame-based capture. So if I'm going to take a picture, it's going to collect information over a set period of time, and then once that period is done, it stops collecting. And so the two images down here on the bottom you see are some of the issues you have with low dynamic range. On the one hand, you lose a lot of information in the bright areas when you try and get the dark parts of the sky in the back of the city there. And then on the other end, you lose a lot of the dark information when you just get the bright lights. So we were looking to increase the dynamic range up to hopefully about 32 bits. Coupling that with high definition really builds a powerful image sensor that you can do a lot with. And by leveraging some asynchronous design, we can actually get frameless image capture. So the typical organization for a image sensor is going to have a sensor array, shown here in red, and some processing logic off down to the bottom. The sensor array is going to be comprised of columns that all have individual pixels in it, and they're going to have some shared logic that allows them to push that down to the processing logic, and you can see the arrows down there at the bottom. Each pixel is going to have 3 major components to it. The photoreceptor, an integrator, basically a capacitor, and then some sort of in-pixel processing. The photodetector is basically photosilicon, and it's allowing you to take light in and convert that into electrons. And then that gets pushed off to the integrator. That will basically functions like one would a bucket in a rainstorm. You collect electrons, in this case water droplets, and you can have small buckets and large buckets, and there are trade-offs there. Your smaller buckets are going to give you more information in the dark areas, but you'll start to see the washing out from the previous slide that you'd see in the bright areas, which is complemented by if you've got a big bucket, you really lose a lot of information in the dark areas. The in-pixel processing can usually ends up going one of 2 ways. Either you can convert the analog signal coming out of the integrator, because it's a pretty analog component, into a digital signal and then push it down the pipeline over on the side, or you can send down all analog signals. And frequently you see cheaper cameras and cheaper sensors use the analog approach because there's less circuitry involved in less circuitry in the pixel, and it's advantageous because you can get a larger photodetector, but you're going to lose a lot of information from noise and other electrical interference like crosstalk. So the prior art for what we were looking to build off of usually uses an approach where the in-pixel processing is going to output discrete events, and then the discrete events are going to be summed up in the logic that's off down at the bottom of the chip. The accuracy here is going to be limited to the number of events that you can record, and that it gives you a very integer-based way of counting things, and it's easier to implement, but has some flaws that I'll get to later. You also, because this is a framed system, are going to lose any partially filled buckets. So if you've got a really, really dark region, you might only get 1 photon, or not even a photon, or say part of the bucket is going to get filled, and you won't be able to dump the entire bucket, which won't generate an event, but there is some information there that you are losing.
What's an event?
In this case, events are one time that the capacitor is going to fill and empty. So every time that empties, it's going to push a signal to the in-pixel processing unit, and that will generate in the analog to digital version. It will send a digital signal down the wire, and that's an event. So the approach that we were looking to take was to combine two things. One, we want to, instead of measuring discrete events, we were looking to measure the time between events. And that allows us to, instead of have a linear scale, we can use the inverse of the linear scale and get a really nice gradation. The asynchronous nature allows us to get away from this notion of frames, and we can really look at the very dark pixels and very bright pixels differently. As I was indicating, so this is what you would see. The prior art here is going to have these discrete steps, and they're going to show that either you'll have a value at 1 or at 2, but since we're using time in between, we can get roughly 10 to the 6th increase in terms of information that we're transmitting, because we can get all of those little steps in between. And time can be measured much more accurately on a sensor than something like discrete events, because for our approach where we're spreading this across plenty of time, we might only get an event or 2 events, those bucket empties, in the time interval, and we know exactly how far apart they are. But if you're only counting events, you only know that there are 2 of them, and they could have been 2 right at the beginning and then a bunch of nothing at the end. So it allows us to more accurately get a calculation on that. So as I indicated, there's intent we were wanting to use an asynchronous design here, and the pipeline is going to look like the diagram over on the side, and it'll allow you to insert events as you need to. This helps both in the frameless sense, but also because when you use an asynchronous approach, you only need components talking to one another when there are things happening, and so you can get advantages in terms of power consumption as well. The dynamic range of our system is going to be determined based upon the maximum number of events that the brightest and the darkest pixels can generate. And the max events in this case is going to be limited by the amount of events that the network on this pixel sensor can use. And so when you hit saturation with that, you start to lose information. The minimum events, since we have this frameless approach, can be longer than a normal frame would be. And so I can set a camera in a very dark room and get information coming just a short amount from the very bright pixels and get a much wider amount of time for the darker pixels and still get information in both regions. One of the tricks that we can do to further increase this is prescaling or decimation. And for this approach, there's a suggested frame that we need to give the sensor. And this, based on the suggested frame, we can say, if the events are coming too quickly to the in-pixel processor here, the comparator, we're able to say only emit 1 event every 2 or every 4. That way we can double, or if you use a larger scaling factor, you can go even further into how much advantage you get out of that. As I indicated, the frameless capture is really advantageous because you don't need to, you're getting time between events. And so because you're able to spread that out between different events, you can also minimize jitter in the photons that are coming in, because they're discrete events coming in at what are functionally random intervals. And so if I get, 3 events, they might come all very quickly, but if I can get these 3 events and I know the time between them, it's going to be a much more accurate value for the intensity of the pixel. So the work that I did was in both the sample scene and the image output here. The functional simulation was something that was mostly Professor Montek's work, and it's a C++ hardware model. There are a lot of things that it does well, such as implementing the hardware logic. At the same time, physical phenomena like crosstalk and noise on the wires are things that need to be predicted beforehand, and then added in as constants to the model. So for this sample scene generation, there were some difficulties because there are no cameras currently that can capture this much information in the scene. So you end up having to generate these scenes from 3D models, and you can't use real-world images. One of the other issues that we ran into was that the file format for having this much information in it is not something that you see in a standard PNG or a GIF, and so we needed to go to a file format known as OpenEXR. And the images you're seeing in the back here are stock images, sample images from their site. And you can see that there's a varied amount of dynamic range that you can get from those. It's an industry format designed by Industrial Light and Magic, and it's supported in rendering tools such as Blender. The nice thing about Blender was the tool chain uses the full double precision floating points for the entire process of calculation. So we didn't need to worry about it being truncated internally before it got output into the single precision floating points that we wanted as output. Another issue with using sample scenes is that you really need to tailor what you're getting if you are looking at a scene. And so this is the scene that we actually used. And I had to go in here and manipulate the lighting sources such that one of them was very bright because the standard dynamic range is scaled so that it would look good on a PNG, and that has a much tighter dynamic range. As you can see, this is an indoor scene. We tried some outdoor scenes as well, and the issue that we ran into was that the outdoor scenes tended to have a much more compressed dynamic range, and you have a lot more control with the indoor scenes because of lighting. Blender has two main render agents that it uses. There's a cycles render and an internal render. The cycles render is much more true to real simulation. The internal render is more of a quick and dirty thing that will output things very quickly. And so the image you see here is a single cycle on the cycles render. And I ran into some issues with runtime where in order to get really good looking images, you need a lot of cycles. And so I'm going to step here through a few of them, and you can see they start getting less pixelated and more, it starts to transition into grain here, and you see the cycles down there on the bottom are increasing up until you get here to 100,000. And the actual calculations we did were in the million range, and it took quite a while to get these. The simulation itself output basically raw unencoded floating points, and so I had to both convert initially the OpenEXR format into a format that the simulation could handle, and then back into the OpenEXR format to display later. And one of the very nice things about the displayer that comes with this open format is that it has a nice exposure slider. So you can display all 32 bits of information, even on something like a monitor that's only going to output about 8 bits. The results that we had, there was an SNR about 60 dB for the prior art. And then, as I indicated previously, we tested both with and without decimation, and that's the scaling factor. And as you can see, the decimation does it does give you better output. I'm going to switch over to the actual viewer now, and it's going to be a stitched image. And on the left, you'll see the prior art, and over on the right is the approach that we had. So that's here. And let me start here, the dark region first. So the prior art, as you can see, is having a lot of issue with the very, very bright lights, because the way that this is displaying exposure, only the brightest lights are being, only the brightest pixels are being shown right now. And so as we continue to step up here, we see that this scene starts to come into view. And if you were to compare this to the other images I was showing you previously, this white region here is the same as the washed out building in front of the St. Louis Arch. And if we keep going, you'll start to see what is referred to as banding here in the corner. And this banding is because of the fact that the prior art uses an integer-based system to keep track of the very, very dark regions. But over on the right, our method does not use this, and thus you see a clean transition with no banding. And that continues up until the image basically just washes out. All right. Any questions?
Questions?
So I have a non-technical question.
Okay.
I was surprised by the spelling of color you used. Your advisors doing?
No. It's the spell check on my machine.
English?
Yeah. Sorry?
I said you learned proper English?
Apparently.
Analog is LOGUE in his slides. Can you explain the dB numbers, what those really mean?
So it's a signal to noise ratio. It's an indication. So we had a sample image, sort of a source image, and so we could compare directly what the sensors should be outputting as a sort of perfect scene as compared with what actually came out of the simulation. And so for the signal to noise ratio,
Let me ask again. So on the left picture, the prior
Yes.
art, you said 60 dB.
yes.
On the right hand side, you said 120 some
Yes.
dB.
And you're wanting, for that, higher values indicate better performance?
Is it just twice as good? Or what does 120 dB mean versus 60 dB?
That's the distinction between the what you're seeing. It's the amount of loss that you're seeing in terms of the very, very bright pixels and the very dark pixels.
So 60 dB means about 1 to 1,000.
Okay.
And 120 dB means 1 to 1,000,000. So the noise in that picture is 1,000 times less.
So from the description in the program, it mentions that you guys are trying for a higher dynamic range for the sensor, about 20 bits, but you also mentioned that you guys were using 32 bits. Is that just a change that was not incorporated into the description?
Functionally, yes. The output format that we're using is floating points. So the simulation, I believe, is using the 32-bit precision floating points. I should probably let Professor.
Well, the file format can handle 32
Yes.
bits. The actual hardware right
Yeah.
now is about at 20 bits or
Yeah.
so.
Okay.
Yes. Thank you.
All right. My name is Colin Arnott. I'm a junior computer science major, and this semester I did some mentored research with Professor Montek and Leandra. So the motivation behind this work is current image sensing has fairly low dynamic range compared with what, say, the human eye can do. Most screens are going to output about 8 bits, and the cameras are going to get probably about 12 bits maximum. And they're also going to be limited to a frame-based capture. So if I'm going to take a picture, it's going to collect information over a set period of time. A typical organization for a image sensor is going to have the sensor array, shown here in red, and some processing logic off down to the bottom. The sensor array is going to be comprised of rows columns that all have individual pixels in it, and they're going to have some shared logic that allows them to push that down, and then once that period's end is done, it stops collecting. And so the two images down here on the bottom you see are some of the issues you have with low dynamic range. On the one hand, you lose a lot of information in the bright areas when you try and get the dark parts of the sky in the back of the city there. And then on the other end, you lose a lot of the dark information when you just get the bright lights. So we were looking to increase the dynamic range up to hopefully about 32 bits. Coupling that with high definition really builds a powerful image sensor that you can do a lot with. And by leveraging some asynchronous design, we can actually get frameless image capture. So the